Welcome back, class. So now we are going to proceed with a problem where we still know what the equilibrium constant is, but instead of knowing one or all but one of our equilibrium concentrations, so that we can just simply plug into our K expression and solve for that concentration like we did in the previous problem, in this scenario, we know the equilibrium constant and the initial concentrations or pressures, but we don't know anything about the equilibrium concentrations. So to do this kind of problem, we're going to have to go back again and use our ice tables. Now, unlike when we used ice tables before, where we knew both initial information and at least some equilibrium, so we could use simple stoichiometry to figure out the magnitude of the changes with numbers, we're not going to be able to do that here. We're going to have to use variables to describe the changes. So, for example, if we look at this equation over here, let's say we have the sample reaction of A goes to 2B, and we know that initially we have 1 molar of B, and we don't have any, of A, and we don't have any B, but we don't know anything about the equilibrium concentrations. But what we do know is that there's a relationship between the changes. So we can define the change in A, say, as X, right? And so we know it's going to go down by X. And we know B, right, there's a 1 to 2 ratio here, so it's going to go up by 2x. So we've defined our changes now not with an absolute number, but with a variable expression. And then, of course, we can write an equation for our equilibrium concentration utilizing the initial concentration and the change. And so our equilibrium concentration here for A is going to be 0.1 minus some change x. The concentration of B, right, is going to be 0 plus 2x, or simply 2x. So now we have expressions for the equilibrium concentrations that we could then plug in to our equilibrium expression, our K expression, and solve for x. And that's the kind of approach we're going to use. Now, before we get, solving a problem, one thing we have to figure out is we had these positives and negatives here. So how do we know what's going to go up and down? Is reactant's going to go up or down? Product's going to go up or down? Well, this is where we have to evaluate Q. So a lot of the examples are going to be one of the extreme instances of Q, where we have either no product or no reactant, so we know which way it's going to go. So for example, in this one, right, we didn't have any product, so we know it's going to move toward product. And we know, so the product value is going to go up, reactants are going to go down, or vice versa. Now, on occasion, you may have a problem where you have both products and reactants, and so you actually do need to quantitatively solve for Q to figure out what direction does it have to move toward K. Okay, so as we go about doing the math, we're going to encounter a couple of different math examples. Right? We're going to find second order equations where we can solve using simple algebra with square roots. We are also going to find instances where we have second order or more complex, where we have to use a quadratic equation. And of course, we're also going to find values that maybe we don't want to solve a quadratic, or they're higher order than second order, and those we'll find out we can do by some approximation techniques. Okay, so let's move on to our first problem. Okay, so here's our first problem. We have the reaction of N2 plus O2 going to 2NO, and we're given an equilibrium constant here of 0.1. Now, we're told additionally that we have initial concentrations here of 0.2 molar N2, 0.2 molar O2, and we have no NO. Okay, so if we go through our process, first thing we have to do is determine which direction the reaction is going to go. So again, this is one of those extremes. So we know we don't have any product, and so our Q, we're going to have our expression is going to have a 0 on top, since that's our products. That's going to end up with a Q value of 0, and that of course tells us we're going to move toward products. So we know the products are going to go up and the reactants are going to go down. Okay. So now let's define these changes in terms of some variables. So if we look at the stoichiometry, we have a 1 to 1 to 2. So we could say that both N2 and O2 are going to go down by X, and NO is going to go up by 2X. So we've kept our 1 to 1 to 2 ratio here. Now we can define the equilibrium concentration using equations, taking our initial minus our change, and we have our initial minus our change, and then we have our initial plus our change, or you can simply write this as 2x. So now if we take these equilibrium concentration expressions and we plug them into our K, we get the NO, so we get our K, or 0.1, equals our NO, okay, which is 2x squared over N2 minus x times O2, 0.2 minus x. And we can now do some algebra to solve for x. And that's what we're going to do next. Okay, let's walk through the algebra here. So I've rewritten our expression here. So we have our 0.1 for K equals 2x squared, put that there, over 0.2 minus x times 0.2 minus x. So one thing we can quickly do here is we can recognize that on the bottom here, on the denominator, we have two identical terms here. Well, we can rewrite that as a square, right? So we can write 0.2 minus x squared here. So what this sets up, right, is we have a square on the top, a square on the bottom. We can simplify that by taking the square root. Now, of course, we have to do that to both sides. So we take the square root of our 0.1 over here on the left, and we end up with 2x over 0.2 minus x over here on the right. So now we can do some algebra, and there's different ways you could write through the algebra here. But I'm just going to first bring the 0.2 minus x over to the left-hand side here. So we get something. So once I've gotten that over here, I'm going to distribute my square root of 0.1. And of course, you could solve for numbers. You don't have to write it out this way, but I'm going to distribute my square root of 0.1 times 0.2, square root of 0.1 times x. Then I'm going to bring my x terms together on the right side of the equation. So I've simplified here to get a number. I've grouped my x terms. So now I have 2x plus square root of 0.1x. I'm going to combine those x terms. I'm going to simplify them into a numeric value here. So we end up with 2.32x on the right side, 0.063 on the left side. We solve for x. We get 0.027x. So now we have that value of x, right? That variable. So we can then plug that x value back in and solve for our equilibrium concentrations using the equations we've had in our ice table. So both N2 and O2 were 0.2 minus x. So if we plug that in, we get value of 0.173 molar for both N2 and O2. For NO, it was just simply 2x, so that gives me 0.054 molar here. So this completes the problem, but one of the things that we should always try to do is to make sure we did our math right. There's a lot of places when we do this algebra that we can make a mistake, but we can do a really simple check, and that is simply to take these concentrations, plug them back into our equilibrium expression to see if we get the same K that we were given in the problem. So if I do it this case, I plug everything in, I get a value of 0.097 for K, which is very close to 0.1. So that gives me a high level of confidence that I solved my problem correctly. Okay, so that's one problem. Now, in the next video, we're going to do another problem where we have to use a quadratic.